Assalamualaikum warahmatullahi wabarakatuh. My name is Riadinata Karmawira bin Sozali. My matric number CN230006. And I am from Group 7. Will explain about introduction. About how a closed loop PID control cooling power works. The main goal is to stabilize the water temperature even when there are external disturbance like changing weather or water flow rates. By doing this, the system not only improves energy efficiency but also helps protect sensitive equipment and enhance overall safety. To make it work, sensors like RTDs constantly measure the temperature and send feedback to the controller. Then actuators such as valve or fans adjust the cooling process as needed. This method of control is not just used in cooling towers. PID controllers are essential in many industries for controlling variables like temperature, pressure, liquid level, flow rate, and even motor speed.
The front, pa- the front panel simulation has several controls and indicators to regulate the flow rate. The knob is used to set the set point for the process. The flow indicator displays the water flow in the channel. The PID values are given to the PID gain block, and then response of the process is recorded on the process chart. The output cluster is used to display the process variable and the set point chosen. The stop button is used to terminate the flow process program. In the block diagram, the set point is provided to the PID controller. The PID controller also receives the PID gain values. The tense range is assigned to the PID block. The PID controller is connected to a valve, therefore a control block is utilized to display both set point and process variable values on the process chart. A feedback node is employed to compare the actual value with the set point. The stop button is a boolean input used to halt the program. And then set point is the actual requirement of the input. PID gains are used to keep the output at the set point, and the timer is used to reduce power allocation, frequency, and memory usage. Feedback is used to transfer the output to the original process variable. The waveform chart presents the output response of the process by using the PID gain value.
So this is the result for when we set the KC to 10, TI to 0, and TD to 0. That means we are only using P from the PID. So as we can see, the rise time we get is 65 and the settling time is 280 and the steady state error is 7.09. So because of we are only using P, so the settling time and steady state error is high.
Okay, my name is Muhammad Sifan. Now I present about effect of variant PIND convention. For the first, proportional gains KP. The controllers respond to the current error between the measure flow rates and the intended set point is determined by the proportional efficient KP. A faster system response and the should rise time are the outcoming of increasing KP. However, aggressive correction may result in overshoot and system instability if KP is set expensively high. Okay. Okay, next the the integral gains Ki by addressing the cumulative error over time. The integral coefficient Ki successfully removes steady state error. The system improves its ability to sustain the attendance flow rate over time as Ki increase, particularly when there are ongoing distraction. However, when the system is approaching stability, the integral action continues to reach to provide error, causing lags and prolonged oscillation. Okay, for the third point, derivative gains. The derivative gain coefficient KD predict system behavior by the considering the range of the chain of error. It acts as a damping force, reduce overshoot and improving settling time, particularly in systems with initial or rapid disturbance. Okay, lastly, the combined PID-F effect. A combined PID controller integrates both proportional, integral, and derivative action to achieve fast, accurate, and stable control in a cooling tower flow system. The professional term reduces the error quickly. The integral term eliminates long-term steady state error, and the derivative term minimizes overshoot and stabilizes the response. Together, they enable the system to reach the set point more equally, maintain precision, and minimizing fluctuation. According to Wong 2023, this combination is more effective to complex systems as fluid flow control, where disturbance and dynamic change occur frequently.
Potentially involved in identifying trends, anomalies, or critical flow thresholds relevant to specific applications. The culmination of this process provided a thorough understanding of the flow rate variations over time, aiding in decision making, system optimization, or further research endeavors. Ultimately, the integration of LabVIEW facilitated a robust, efficient, and insightful flow rate analysis, showcasing its prowess in data acquisition, processing, and interpretation within scientific and engineering contexts.